So let's just talk a little bit about the specific circuit analysis of parallel resistors. Let's say that we have two parallel resistors or more. So the ... indicates maybe three parallel resistors or four parallel resistors. And let's just give these numbers sequential numbers R1, R2, R3, R4, etc. Say the potential difference of the power supply is delta V. And we can do a circuit analysis of this circuit, delta V. We can do a loop, delta V minus I1, R1 equals 0. Delta V minus R2, R2 equals 0, etc. Yeah, I'm just drawing in the currents. And I did the bottom loop and the top loop, right? So we just did this loop and this loop. Okay, I'm going to undo those. And so you could do other loops too, but I just did those two loops. And notice what that tells me. That tells me that the potential difference across R1, which is this here, is equal to delta V, and the potential difference across R2 is equal to delta V. The potential differences across things in parallel are all the same, right? So delta V equals delta V1 equals delta V2. The potential difference across all things in parallel are equal, because what I put in the boxes is the potential difference across resistor 1, right? By Ohm's law, V equals IR. Potential difference across resistor 2, V equals IR, delta V2. So this is delta V2, this is delta V1. Okay. And this would be true if there was a third resistor, a fourth resistor, a fifth resistor in parallel. All this still holds true. We just have one equation for each resistor that we add. We'd have one more loop, and we would have one more equals dot, dot, dot. Dot, dot, dot. Okay. Notice that. So that's, I'm not sure whether I was talking or not, but hopefully I was. I talked through everything. I didn't have it paused. Okay. So what about the junction rule? The junction rule would show that if I just have the two in parallel, then I from the battery is equal to I1 plus I2. But if I have a third one, then we're just going to split off I3. And then if I have a fourth one, we're going to split off I4. So the currents for the things in parallel add, because as we add something in parallel, we split off a little more current. And I equals I1 plus I2, or plus I3 plus I4, etc. And then we want to combine all of this, and we can go ahead and divide both the left side and the right side by delta V. So I'm going to divide the left side and the right side of the current rule, of the junction rule. I'm going to take, therefore, I over delta V is equal to, and that's delta V of the battery, is equal to I1 plus I2 plus dot, 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 over delta V, so that therefore I over delta V is equal to I1 over delta V plus I2 over delta V plus dot, 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 I3 over delta V plus I4 over delta V. So therefore, I'm going to have to go to a new page. Therefore, I over delta V is equal to, let me go back and point out that I1 over delta V is just R1, right? Because I1 R1 is delta V1, which is delta V, right? So this the quantity, let me do a different color box. The quantity in the purple box is just R1, and the quantity in the second purple box, is not R1, but 1 over R1. The quantity in the second purple box is 1 over R2, because, let me just write over here, delta V1 is equal to I1 R1, so therefore R1 is equal to delta V1 over I1, and delta V1 is just delta V over I1. So this quantity here must be 1 over R1, and this quantity here is 1 over R2. So what we end up getting is I over delta V is 1 over R1 plus 1 over R2 plus dot, dot, dot. And what is this quantity on the left? That is 1 over R equivalent, right? That is the total potential of the battery, right? R equivalent is defined by the total potential of the battery divided by the total current of the battery. So it's for the battery, right? It's the equivalent resistance if the battery was serving one resistor. That's how the definition of the R equivalent, delta V over I for the battery. So 1 over R equivalent is 1 over R1 plus 1 over R2 plus dot, dot, dot if there's more in parallel. We've already seen that, but now I've proven that. The equivalent resistance for resistors in parallel goes as the inverses, the sum of the inverses. And this is true for any resistors in parallel, even if they're in a circuit with other things. We can always write anything that's in parallel, we can reduce it down to an equivalent. So, for example, if I've got some resistors in parallel that are then in series with something, we can still say that this pair of resistors are in parallel, and we can therefore write this circuit as equivalent resistance like that, where that equivalent resistance is the equivalent of R1 and R2 in parallel. So if you don't know a resistor's resistance, who do you ask? Sherlock Ohms. Ha ha. Sherlock Ohms. Get it? Ohms, not Sherlock Holmes. Okay, never mind. Okay, so what about circuit analysis for series circuits? So we're going to do a similar kind of circuit analysis for the series circuit. Let's start with a loop rule, right? The loop rule, if I do this loop here, going in the clockwise direction, we've got plus delta V as we cross the battery, and then the current leaving the battery we'll call I, and there's no junction, so the current doesn't actually change, so we don't actually have to really, we could write I1, R1, I1 and I2 and I3, but they're all just I because it's in series. Although if it's in a more complicated circuit, it may not be, but the things in series all have the same current. So let's just go ahead and write delta V minus I R1 minus I R2 minus I R3 minus dot, dot, dot. And I actually don't have R3 here. I'm just the dot, dot, dot indicating I could have more in series equals 0. And we can simply, if we started with I1, I2, and I3, we said that the current through each resistor is independent of each other, but then we recognize they're in series, so therefore I equals I1 I equals I1 equals I2 equals I3, because there is no junction, so the current doesn't change. So therefore, and I know I've gone backwards, but delta V minus I R1 minus I R2, I keep on messing up. So I end up with that, and then I can go ahead and factor out the I, R1 plus R2 plus dot, dot, dot. However many resistors we have equals 0. And so therefore, I can go ahead and divide both sides by I. So I've got delta V over I minus R1 plus R2 plus dot, dot, dot equals 0. That's just dividing the equation through by I. And so therefore, delta V over I equals R1 plus R2 plus dot, 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 as many as you have in series. And again, this quantity here is the equivalent resistance of the circuit. It's the potential of the battery divided by the current from the battery. And so that is the equivalent resistance by definition, right? Our equivalent is defined as the potential difference of the battery divided by the current from the battery. And that is the resistance as if the circuit was a single resistor. So resistors in series combine, and we already knew that. We can just sum them up. So we're saying that those two circuits are the same. That's what we're saying. Okay. So that's the circuit analysis of series and parallel circuits. So what we want to do next is do more complex circuits and do some specific numerical examples. And we'll go ahead and do that. next. We'll do that next time.